We've seen that stars come in different colours and different sizes, from the most common small, faint red dwarfs to incredibly bright blue hypergiants. But different stars have different end states. Stars like the Sun bloat up to become cool giants, and that strips away the outer envelopes of those stars, and what's left behind is kind of the dying core of the star. And that dying core is incredibly hot and can illuminate the material around the dying star. These are called planetary nebulae. This is the cat's eye. These things aren't to do with anything to do with planets, but it's just what historically they were called. But it's almost ironic that these are the most beautiful objects in the night sky, signaling the death of a star. This is the butterfly nebula. So in the center of these objects is a star, a stellar corpse, effectively, which is incredibly hot, and it just illuminates the material around it. This one is the Eskimo Nebula. Maybe you can think of better names for these things. This next one is the Hourglass. And we see these things in different projections, and so they all look incredibly diverse. When low-mass stars die, they just leave behind a corpse. It's called a white dwarf, about as big as the Earth, but as massive as the Sun also, and it just fades away. It cools down and just fades away. If we now turn to the highest mass stars, some towards the end of their life also put on a beautiful nebula. This is Eta Carina in our own Milky Way, the most massive stars in our own Milky Way galaxy. But the key difference between a big star and a small star is the big ones go out with a bang. The star pointed to there is a star in a nearby galaxy whose light we saw die as a supernova 27 years ago. It was a naked eye object, even though its distance was 170,000 light years. And when they die, the envelope's disrupted, producing what's called a supernova remnant. And that supernova remnant contains extremely dynamic, hot gas. This is the Crab Nebula, resulting from a supernova explosion we saw 1,000 years ago. And the gas in here is still incredibly hot, typically many millions of degrees. In the center of the Crab Nebula is a spinning neutron star, as massive as the Sun, but as small as a city. And it's spinning around so fast, it's spinning around as fast as a blender in your kitchen. So supernova, incredibly bright. Massive stars produce supernovae. Some small stars, when the white dwarf gets too heavy, also blow up, producing a different type of supernova. This is one that Kepler discovered 400 years ago. This is a supernova remnant from an older supernova in our nearby galaxy, the LMC. Really massive stars don't leave behind neutron stars. They might leave behind a black hole, which is an even smaller, denser, heavier thing than a neutron star, so dense that even light can't escape. We can't see black holes directly, but we can tell they're there because of their influence on a companion object. Here on the left, we have a disk around a black hole, and the companion star and the black hole are in orbit around each other. So we can see the motions of the companion star, and we can then get a weight to the black hole. And most black holes around other stars are between 10 and 20 times the mass of our own Sun. We'll come on to bigger black holes later. Supernovae are incredibly bright as galaxies, but there are explosions even brighter. This is a simulation of a pair of merging neutron stars called a gamma ray burst. There's another type of gamma ray burst which relates to the death of a massive star, producing jets formed in the center when the black hole's forming. And these are so bright, they emit as much energy in a few seconds as a supernova does over the course of a few months. So we're now halfway through our journey through the cosmos. So next, will turn to our own home galaxy, the Milky Way.